Well, good afternoon, everyone, and welcome to the HamSCI Telecon. Thank you, everyone, for coming. Today, on the main item on the agenda is going to be Dr. Dev Joshi, our postdoc, who's been looking at Chirp Ionosondes. So he's going to show us some of that data. And I want to get into that rather quickly, so I won't do a whole go around today, but I will ask briefly, is there anyone who has anything else they'd like to put on the agenda for today or any announcements? And nothing heard. So with that, what we'll do is we'll go on to Dev. He'll give his talk, and we can have a discussion about that. And any time left will be open for open discussion. So take it away, Dev.
Thank you. So maybe I shall start by sharing my screen, okay?
Sure.
Okay.
Dev, your audio is a little bit muffled.
Is it better now?
Yeah, better.
Yeah. I'm talking from my phone and it will away, okay?
Yeah, that was not good. You're back to being muffled.
Hello? Hello?
Yeah,
Good?
we hear you.
But muffled.
Yeah, it could be a little better. Nathaniel, what do you think?
I think it's okay.
All right.
Okay.
Rock and
I'm
roll.
connecting through phone, okay? So good afternoon, everybody. I'm Dev Joshi. I am a postdoctoral research associate at the University of Scranton, working with Professor Nathaniel towards a project to build personal space weather station. And today I'll be sharing some early results from the project so far that we have tried to implement in Scranton. The title of my talk is Developing an Ionospheric Sounding Mode using Chirp Ionosondes of Opportunity for the HamSCI Personal Space Weather Station status and early results. The work is done by me along with my advisor Nathaniel, Bill Lyles, Juha Verinen, and Ethan Miller. So before we go, let me start with the outline. I'll try to introduce the idea behind the project, and I'll discuss what is HamSCI Personal Space Weather Station. Then I'll discuss about the methodology used to collect the data at our place, and I'll share the results from our station. I'll discuss those results and I'll point towards the future work that we would like to pursue. Finally, I'll summarize. I think it will be a brief talk. As I go along, I may request Nathaniel's feedback to explain few of the points. So to introduce the objective of the HamSCI Personal Space Weather Station is to develop a distributed array of ground-based instrument nodes, which are capable of remote sensing the geospace system, so that it can probe the ionosphere at finary scale in both time and space. The goal is to gather observations to understand the short-term and small spatial scale ionospheric variability in the ionosphere thermosphere system, so that it can analyze a host of geophysical phenomena of interest, such as traveling ionospheric disturbances, geospace storms and substorms, ionospheric absorption events, etc. Such a distributed array of ground-based multi-instrument nodes will create an unprecedented opportunity to analyze the ionosphere at finary scale in both time and space. It will also provide a big picture view of phenomena that were previously observed only by point measurements. At Scranton, we are trying to implement Chirp Ionosondes node of the Personal Space Weather Station, and it is being implemented on an ATUS and 200 universal software radio peripheral using the open source GNU Chirpsounder data collection and analysis code developed by Juha Verinen at the from Norway. So what is HamSCI? HamSCI is a collective created and led by Professor Nathaniel that allows university researchers to collaborate with the amateur radio community in scientific investigations. The objectives of which are to advance scientific research and understanding through amateur radio activities, encourage the development of new technology to support this research, provide educational opportunities for the amateur radio community and the general public. So what is HamSCI PSWS? The HamSCI Performance Space Weather Station is a multi-instrument ground-based device designed to observe space weather effects, both as a single point measurement and as a part of a larger distributed network. This is a collaborative project under the HamRadio Science Citizen Investigation Collective, led by the University of Scranton, with collaborators at Case Western Reserve University, the New Jersey Institute of Technology, NJIT, the University of Alabama, the MIT HamSCI Observatory, Tucson Amateur Packet Radio TAPR, and volunteers from additional universities and the amateur radio community. The PSWS comes in two flavors: a performance-driven FPGA-based software-defined radio version, which is Tangerine SDR, and a low-cost version, which is Grape. So let me discuss the architecture of the Performance Space Weather Station. At the heart of the Performance Space Weather Station is a software-defined radio receiver with frequency coverage from approximately 100 kilohertz to 60 megahertz. This is so chosen to cover both medium and high frequency band, which are from 300 kilohertz to 30 megahertz, which are particularly sensitive to variations in the ionospheric state. And the output of this SDR is generally raw IQ data, which can be processed into a variety of data products, such as entire HF band of spectrum snapshot, Doppler shift measurements from standard stations such as WWV, signal analysis from Ionosondes, digital signal analysis from amateur radio. Also, the signals received by SDR can be used for HF noise characterization and lighting detection. As we said, this would be multi-instrument. This will be connected to a computer, which can work as local user display, local data reduction, and send that data to a central server, like here. These are like future goals. We are not at here, and our dual frequency global navigation satellite system receiver chip will be used to serve as a highly stable frequency reference, and our ground magnetometer, which will provide 3-axis magnetic field measurements at a 1 second cadence with with about 10 nano Tesla resolution. And the system is modular, which would mean that instruments can be added or removed as needed. For instance, in high latitude for high latitude users, the auroral camera could be added. So it depends upon where the users are and what their needs are. And this is an ongoing project. And these SDR observations, yes. So let me briefly discuss about the Tangerine SDR. The performance characteristics of the scientific software-defined radio being developed as the Tangerine SDR by TAPR, Tucson Amateur Packet Radio. It consists of a data engine with these given specifications, and these are the features. A radio frequency module, these are the modules, and a timing module. The data engine includes of 50,000 logic element FPGA, field programmable gate array, 512 megabyte of RAM, gigabit Ethernet, and can support up to 2 terabyte on a micro SD card. The data engine will be able to simultaneously support 2 separate radio frequency module, RF modules. The RF receive module features dual synchronized 14-bit 122.88 MSPS analog to digital converters with dual SMA antenna connectors as input. It includes remotely switchable attenuation or 20 dB low noise amplifier or fixed 55 megahertz low pass filter and onboard 50 ohm calibration noise source and a place for an optimal user-defined plug-in filter. The GNSS timing module will be dual frequency to provide precision time stepping with 10 to 100 nanosecond accuracy and a frequency reference accurate to parts in 10 to the power 13 over 20 hours. So more information is available at tangerinesdr.com. So the ultimate goal is to have Tangerine SDR as the software-defined radio in the Hello?
Go ahead, Dev.
Yeah. So at Scranton, we are trying to develop an ionospheric sounding mode that will be implemented on the performance-driven Tangerine SDR model. The mode currently being implemented is Juha variant's GNU Chirpsounder 2, which generates oblique ionograms from FM chop Ionosondes signals of opportunity. So these are the this is an example of the ionogram that we processed using the Chirpsounder 2 software, showing the single hop and the multi-hop propagation of high-frequency radio waves transmitted from relocatable over-the-horizon radar site in Virginia to Springbrook, Pennsylvania, the receiver site. That's the house, Nathaniel's house, and this data is from November 17, 2020. So the methodology consists of the following steps. The software Chirpsounder 2, which is open source, available in the GitHub site of Juha variant, can be used to detect the Chirpsounders and over-the-horizon radar transmissions over the air, and we can calculate ionograms from them. The software relies on digital RF recordings of HS. This is a new implementation of the GNU Chirpsounder. This new version allows to automatically find chops without knowledge of what the timing and chop rate is. The process starts with the data capture with Thor, which comes with digital RF, a USRP N2 cross 0, a GPS DO, and a broadband HF antenna. The following parts of the Chirpsounder 2 software are then implemented to plot the ionogram. There is detect chops.py, which is used to find chops using a chop rate match filter bank, and there is find_timings.py, which is used to cluster detections and determine what chop timings and chop rates exist, and calc_ionograms.py, which is used to calculate ionograms based on parameters, plot_ionograms.py, which is used to plot calculated ionograms. So this is the experimental setup. This is an image of the Universal Software Radio Peripheral N200 kit. The image source is taken from the Ionosondes website. This is the location, receiver location. This is the arrow that I'm trying to show here. Springbrook in Pennsylvania. That's Nathaniel's house. The location was chosen because it has a better RFI environment instead of the urban setting at the University of Scranton, which has like more noise. And this is the antenna that we used. This is the GS6B KW multiband HF antenna employed in receiving the HF signals at the receiving station. This is where the image is taken from. So implemented on Intel Core i7 with 64 GB RAM at a USRP N200. Receiver located in Springbrook. Antenna is GS6B KW. So two ionograms showing the reception of chop signals transmitted from the rotor site in Virginia and received at the receiver location. In above images, signals transmitted from the transmitter site in Virginia have been received after single hop. You can see this is a single hop reception from F layer. This is double hop. This is triple hop. This is fourth hop. So single hop and multi-hop receptions are seen in this image for both of them. Both of them are for November 13, before by some time. And this is, as we learned, ground scatter from, it could be from, this is scatter from ground or sea. And I made a video for one of those days, November 17, and I would like to show the video. You can see it progresses in local time. Local time, yeah, it's in the evening. So that's around close to midnight, right? Maybe we can play it one more time. So after midnight, it gradually builds around 2. These are like post-midnight increase in the density spread. Around 8, it starts building up in the morning. The ionosphere starts building up. This is through the day. And around in the evening, it will start decreasing. Around 5 p.m. in the evening, it starts decreasing.
And so one of the things that we're seeing here in that video, I just want to point out really quickly, if you go back to that video for a minute, Dev, you can see the FOF2 or that peak F frequency vary back and forth with time. And that's an example of a traveling ionospheric disturbance moving through the field of view. So it moves both up and down in range offset, but it also moves up and down in frequency along the x-axis.
Mm-hmm. Right here.
Yeah.
So we tried to model, this was the initial stage of our investigation. We have made some progress. So we tried to model those observations, and we use ray tracing to model the observations. We use the ray tracing package, HARLab. It's developed by Manny Cervera and his team at DSTO in Australia. So the geometric path length, which is the actual distance traveled by the radio waves as calculated in HARLab ray tracing for the 5 megahertz radio wave, is 530 kilometers and 720 kilometers respectively for the first hop and second hop reflection from the F layer. So this magenta is the reflection from the F layer. And this is first hop, as we can see, and this is second hop. Oh, sorry. And this first hop distance is 530 kilometers, and the second hop distance is 720 kilometers. These values compare very well with the one-way range offset calculated by Chirpsounder 2 as seen in the ionograms for the first hop. For the first hop, that's very close, around 530 kilometers. When the second hop is not around 720 kilometers, it is higher. So this value is less than what we see in the ionogram processed by the Chirpsounder 2. So we can say we successfully modeled the first hop, but with the second hop, there was some discrepancy, and it was a work in progress. And let me discuss the results and go in the direction of the future work. So in this research work, we presented early results of top Ionosondes observations made by a module of HamSCI PSWS located at Springbrook, Pennsylvania. In particular, we saw the high-frequency radio wave transmitted from the Rother station in Virginia as received by the PSWS and processed using Chirpsounder 2 software. In our preliminary modeling work of the HF propagation along this path, it is found the modeling results match very well with the first hop transmission as observed in the Chirpsounder observations. The results for the second hop transmission show some difference between modeled and observed results. Understanding these differences would constitute an element of future work in this project. In the future, we would want to optimize processing chain for lower cost of computers, develop techniques for triangulating Ionosondes transmitter locations using PSWS network, implement Chirpsounder 2 on Tangerine SDR, HamSCI PSWS hardware, analyze Chirpsounder observations to understand the short-term and small spatial scale ionospheric variabilities in the ionospheric thermosphere system, establish a network of oblique receivers around Chirp transmitters to analyze mesoscale ionospheric structure. So this is my summary. HamSCI PSWS is a distributed array of small instruments project for making geospace and ionospheric measurements for both citizen scientists and the professional research community. FM chops Ionosondes are widely distributed around the world and serve as a signal of opportunity for the generation of oblique ionograms using PSWS hardware. We have implemented a proof of concept receiver station using GNU Founder 2 software by Juha. I would like to acknowledge the support of NSF grant AGS 2002278, 1932997, 1932972. GNU Founder 2 is available from GitHub site of Juha. The results have used the modeling was done by FarLab ray tracing toolbox created by Dr. Manuel Cervera at DSTG, Australia. This is available by request from the author, and these are my reference. Thank you.
Thanks a lot, Dev. Are there any questions?
Question for Dev concerning the picture that you showed for the model of the space weather station for Tangerine. That one.
This one?
Take out the lightning detection for the software-defined radio. We took that out.
Yeah, that's probably a good idea.
Okay.
Small detail, but I
Okay.
don't want to cause any questions down the road. Where is this?
We had discussed doing lightning detection through RF, but we took out the actual lightning detector, as I remember.
Right.
Right. Yeah, I think when I made that diagram, it had a lot of things that could be features. So yeah, I could see lightning eventually happening. It just I don't think anyone's developing it right now.
Okay.
We certainly can add it, but for the first shot off the bow, that's probably not a good. It's not going to be there.
So I actually Dev, that was great, but I actually want to have you show some people some of the plots you just showed me even this morning, because you've actually taken this presentation another step, or you've started to. And so can you show some of those?
Could I ask a question about the hardware before you get off the slides?
Yes.
Looking at the computer that you have attached to it, further down where you were saying Intel i7 and whatnot.
Over here, yeah. This
I think it was the next slide.
This one?
No, not that slide. Where you actually showed what you're using, not the Tangerine SDR spec.
The Edis one?
Yes. No, further down. Later.
Dev, where's the one that has? Yeah. Where's the one that has the picture of the Edis? That one, yeah.
That one.
This one?
Yeah, you're saying implemented on Intel Core i7 with 64 gig. Are you using all of that RAM? Are we going to need that big a computer to do this work?
That's a good question.
So the reason we have that much RAM is because we're creating a RAM disk.
Right.
And we are saving the last 5 to 10 minutes of the 25 mega sample per second spectrum to the RAM disk in a ring buffer.
Right.
And then if the software detects a chirp, then it will go back in time and de-chirp it.
Uh-huh.
Now, for this is what Juha calls serendipitous mode.
Right.
So what Juha said is that if you already know the time schedule of the chirps and you have a GPSDO, you don't need to run the ring buffer. You can just de-chirp it when it comes in.
Right.
But we don't know the time schedule of all of the chirp ionosondes ahead of time. So we have to detect it. But
how often do they generally chirp?
The ones that Dev is looking at is 12 minutes.
Oh, okay. So you're trying to hold how long? Oh, you said about 25 minutes?
Well, no, about 5 minutes. So
5 minutes.
So the thing takes about I think it takes The chirp rate of this is what, 100
kilohertz.
kilohertz per second, was it?
Yes.
Yeah.
Yes.
So I think it only takes about was it 5 minutes?
3
6
minutes.
minutes?
3 minutes.
3 minutes for the actual chirp, but the chirps are spaced 12 minutes apart.
Right. But you said you have a large ring buffer, and did you say 25-minute buffer?
No, 5 to 10
Just
minutes.
a 5 to 10-minute buffer. Okay.
Yeah.
Because I was wondering if you were trying to capture 2 chirps within the buffer.
Yeah. No, we're only capturing
I
one
see.
chirp.
But once we know the timing, you don't need as large a buffer.
That's right.
I mean, that's just a very large computer to ask everybody to hang on to attach
The
to.
idea
This.
is that it will work as a central system, which will provide the schedule to others.
Okay.
Yeah, because the schedule doesn't change every day. It changes every few days at we think random time, is it?
Yes.
So the idea is that we'll have a couple computers or one computer that has that's a big computer and has this ring buffer going, and it'll keep detecting things and monitor the schedule. And it will create a schedule file that it can post to the internet. And then other computers can monitor that web address and then download the schedule. And so you might end up missing 1 or 2 chirps whenever they change the schedule, but then you'll get the rest for the rest of the day.
Oh yeah, that'll be useful.
Yeah. So that's one of the things we're working on now.
And
Dev,
the other question I had is, what differences might there be between this implementation and then when we do it on the Tangerine SDR? Are we going to try to implement more processing within the SDR?
Yes. So the actual dechirping, we want to move on to the FPGA.
Right. That's what I thought.
Yeah. Because right now, we have the EDIS connected directly to its own dedicated NIC on the computer, and it basically saturates the gigabit line.
Exactly.
So you're not going to be able to. So I think a small Raspberry Pi is not going to be able to handle that kind of dechirping or that bandwidth constantly. John's agreeing here.
Mm-hmm. Right.
Yeah. So Dev has written some software, a script to start analyzing the decodes that our machine has already done and then generate a schedule file. So now we have to work on actually implementing it in real time and testing it.
Now, does the USRP, it does not have the computing power to do that internally, or are you just jumping to the new receiver?
It probably does, but Juha is the one who developed it, and
right.
He's of the mind that, it's just I'm primarily a scientist, and I'm gonna do it quick and dirty in Python and C, and so
Right.
I don't want to mess around with like Verilog or, FPGA images.
Yeah, I was just wondering if that could be developed before the Tangerine is online using USRP.
Nathaniel, were you
probably could.
Were you trying to suggest me to get these images?
So, Dev, I just want you to explain to people what this image is and how you got it and why we're doing this.
So we're trying to. So we have collected this data for quite a number of days, like 15 days perhaps, from 12/5 to 12/23 up to count. So good number of days. And I went through manually, observed through those ionograms and captured the height of the F layer and the maximum value of the ordinary F layer. So this frequency of ordinary layer, and we see how they vary. And when they are varying, like now we're at a stage how we can detect out of this variation PIDs. So there could be diurnal variation, and the idea now is to subtract those find the best way to subtract the diurnal variation, and after the subtract, if we continue to see variation, which could possibly be TIDs, and find those parameters. That's what, and I did that for the height as well, and we see the variations for both of them. So I will now at this stage to fine tune this process and choose an algorithm to do the filtering, and then look for the signatures of TIDs and what possible parameters of TIDs can I expect from these observations.
I think one thing you can do to start off with, Dev, with this is just plot each day individually. So it's nice having this summary plot, which kind of shows you where your data gaps are and what the overall trends is. So keep this, but in addition to that, make individual plots for each day, and then it'll be easier to see the diurnal variations, and the things like TIDs, they'll become more evident because they won't be so scrunched together.
Okay.
Especially you do a video concatenation of them, have an animation going day to day, and just keep plotting them and showing them change day to day, like we were doing for the WWV plots.
Yeah.
Okay.
So
Nice
it's
job,
nice.
Dev. Very nice job.
Yeah. So it's nice as you're starting to reduce that data into something that is tractable.
Okay.
And then as we get more of these stations deployed, we want to be able to try to sense which direction the wave is going. And so I sent you a couple papers today that have some different techniques of some of the ways you can do that.
Yeah.
Once we have multiple receive sites.
Mm-hmm.
And similarly, we're going to do similar things with the Grape.
Okay.
Any more questions for Dev? And then, so Gary writes in the chat here, question on TIDs. Are they short-term events, minutes in duration, or long-term events, hours? Recalling Dev's video, the apparent TIDs appeared to me to be lined up with the time of day. So TIDs are actually categorized into two different categories. We have medium-scale traveling ionospheric disturbances and large-scale traveling ionospheric disturbances. And the medium-scale ones, they have periods between 15 minutes to say an hour, and you can see them. You'll see them go through an entire afternoon. So the period's 15 minutes to an hour, but you can have an event where you've got multiple, wave pulses or waves going through over an entire afternoon or longer. And then, so I guess the answer is they're on the order of hours. Now, your large-scale traveling ionospheric disturbances, they're going to have periods between about 50 minutes and 3 hours. And you could see, 1, 2, or maybe 3 of those wave peaks in a row. Kristina, do you want to show some of your plots too? Because you're on a similar theme.
Thank you so much, everyone.
Thanks, Dev.
For listening to me.
Need to unmute, Kristina.
Thank you. Golly, which ones? I don't know if I have any queued up at the moment.
You could show. Well, one thing I thought was interesting. You're trying to split. You're trying to look at the actual vertical incidence Ionosondes.
Yes.
Yeah. So Kristina's problem. Why don't you explain your problem? And then
sure. Yeah. So this is this code is like 30 minutes old. So it's very much in the middle of things. Let's see here. Okay. So here's what I have previously. This is for October 1st from the Festival of Frequency Measurement. We're putting in some edits to that paper, and this is the DID base Lowell Ionosonde network, the data that's pulled from their webpage. So this is for the one in Alpena, which I have a map someplace. And I'm trying to figure out how to validate our stacked plots from the festival frequency measurement, which you guys have all seen before, against this. So I'm looking at the period of these variations. I guess these are the daytime variations, these are the nighttime variations. Do I have that right? Yeah. And determining whether they are in keeping with what we picked up with our experiment.
Could we have Dev mute his mic? We're getting an echo through there.
Okay.
Thanks, Deb. So I'm trying to figure out the period of those variations, and I've run an FFT. This is for the whole thing, but everything just sort of gets smushed. And then I'm cutting down the time period and running it. But I think it might just be like there's just not that many data points for this particular one. So I'm going to try it with a different Ionosonde. But
Yeah.
I'm trying to figure out, like,
You showed a plot this morning, Kristina, that had kind of all the Ionosondes.
Yes, I did. 1 second. Let me get that pulled up. I don't have that one, unfortunately, in stacked plot form real quick, but I do have it in image form.
I just have another place we could look for oblique sounding data too.
Yeah, what do you got?
Super darn.
Yeah,
and that
that's
will
true.
go, and you actually have a better chance of getting something that's a measurement that's over that particular region that you want.
Yeah,
But,
that's a really interesting idea. I know from Simon Shepard that they're doing some bistatic tests, which require actual timed transmissions, where when they're using just one radar, they don't really care when the pulse goes out. So you might need the bistatic tests to get a good sounding out of it, but you're right.
I don't think, for what I'm thinking of, I don't think you're going to need the bistatic. I think you can you'll actually be able to start seeing these things just in the RTI plots that they get right off the website. So I could help you find that. But I guess what I was looking at here, so that's FOF2.
Yeah.
So I just noticed there's a lot more like wave activity, it seems like, happening during the daytime hours than during the night. And what's striking to me is that your Doppler, your festival frequency measurement, is the opposite. Can you put your festival frequency measurement figure on the same, so one right next to the other?
Yeah, let's see. Do I have that handy?
Uh,
Just pull that up.
question.
Yeah.
Yeah.
On your sources there, you had Alpena. I assume that's Alpena, Michigan. What's transmitting there?
There's a Digisonde Ionosonde.
Here's the map of every spot. Yep, there you go. Here's the map of all of the Digisonde Ionosondes that collected data on that day.
So it's not transmitted to receiver.
No, it's both actually.
Well, it's both, but the thing is, it's pointing straight up. So what I have is I have a bunch of receivers that are all collecting from WWV.
Is that a private one in Alpena? Is that privately owned?
I forget who maintains the network.
I think they're all.
Lowell?
Well, UMass Lowell is the main vendor. They're the ones that design these things, sell them, and run the main website. But the actual instruments are not necessarily owned by them. They could be DoD. They could be like USGS. They could be they could belong to a university. So it's usually not a private individual, but often a government entity, a research institution, or a university.
Yeah, because there's an old military base there. I think it's an Air Guard base now.
That's probably why it's there.
Yeah, there might be some info in the metadata about that stuff.
Okay.
I have a script for collecting it where you can plug in a date and it'll spit out all these plots. So you can say, you know, give me everything between a certain Latin lawn that collected data between these two times, and it'll scrape the website.
Okay. Yeah,
But,
because otherwise there's really nothing up there.
right. So what I'm trying to do, you know, I'm sorry for this being fuzzy. I'm sure it is for you guys, but here's all of my squiggles from that day, right? And you can see that those are marked for the locations where people took them, which is the same that are on the ones in this this video map down here. And what I'm trying to do is figure out a way to validate these squiggles according to these squiggles in a way that will appease reviewer 2. And so that's what I'm trying to sort out is if we can find similar variations that are aligned. Unfortunately, what I don't have is I don't have a thing where we have, you know, WWV, a receiver, and then a digisign immediately in between, or in fact anywhere near the midpoint. So because the closest one perhaps is I have a couple of stations that have their midpoints somewhat close to the Idaho National Lab Ionosonde, but it's really kind of far off. And one of those data sets I had to throw away because there was too much drift. So I don't have a really good exemplar is the thing. What I do have is a whole bunch of squiggles that all squiggle in approximately the same way.
Another thing you can do to help appease the reviewers that's relatively easy is I sent you a number of references today. And some of those references actually essentially use exactly your technique, except instead of using amateur instruments, they're using professional instruments. So you could reference those at the beginning to say, this Doppler technique is used by bop, 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 bop. And then you can say, these are professional implementations. Here's an amateur version of it.
Right.
And that at least gives you some more theoretical footing that because I think that's one thing the paper is kind of missing right now is that link back to why does this theory actually work? And with those references I sent you, you can start to build up that chain.
Yeah, the reviewer has essentially, what they've asked for is validation against either Ionosondes or IRI. That's what they've specifically requested. And I'm trying to figure out like which one of those might be worth pursuing, because the thing about IRI is that the interesting thing here is all the short-term variation, and the IRI isn't going to show that. It's all going to be smoothed out.
Right, but it will show the dawn-dusk transition.
That's true. And I can point out the dawn-dusk transition, which, you know, I would say kind of speaks for itself. Here, you can see that there's always this bump right after the dotted red line in the middle, and that's local sunrise for the stations.
So for the reviewer, you just need one of these things.
Yeah.
Yeah.
And I don't really know which one's more effective. I've spent some time pushing on each of them, and I'm kind of not wild about the results I'm getting for either.
Right. Now, well, Steve, did Steve Serwin come back with any new results on doing his reverse Doppler height change estimate?
He mentioned this morning that he was poking at it. I don't know. Is he in the room here?
I am. I'm here, and I have it transcribed. And if I hadn't spent so much time on Zoom meetings today, I would have had it done by now.
I know that feeling, man.
Me too.
But anyway, it's all in Excel, so all I have to do is do the, you know, integration by parts and see what the answer is.
All right. Well, I don't want to monopolize the meeting, but maybe we can stick around after we wrap up here and spend a little time talking about it together.
Sure.
Yeah, and in terms of which way to go first, Kristina, it's whichever one gives you the better result fastest.
Fact.
So if Steve's approach wins, that's the one.
Yeah, that's why I'm curious to hear about it.
I want to get to the super darn, but I want to stay away from it for the moment because I don't have my toolkit up and running. The last time I ran that analysis code was in 2016 for my PhD. And part of the funding for my new grants includes buying new computers, hiring students, and getting that code up and running again and getting access to that data again. So if if we can't find anything else, what we can do is I can show you, we can actually look at the date on the Virginia Tech SuperDarn website, and we can get the graph up, and we can see if the wiggles there match here. I mean, we can do that right now if you want.
I think that would be good. Is there anything else that people in this meeting need to cover before we might do that?
I wanted to ask a question that maybe Dave McGaw has some thoughts on, because he has a lot of experience with it. You can actually put that back up on the screen.
Okie dokie.
So put your, so have that one on the right, and then put your Ionosondes up on the left.
All right, which one you want? HMF2?
I think FOF2.
Let's see here.
Let's see if we can see them both at the same time.
Time to play the old tessellating figures game. That's not correct.
By the way, to answer Alpina,
correct.
it's an Air Force asset.
Oh, thank you. There's probably some interesting stories behind some of these. All right, so here we go.
All right, so I guess the thing that I was curious about is I noticed on the FOF2 plot, everything is rather quiet between 0 and 12 UT. And there's more activity between 12 in the afternoon after 12 UT. And in the Doppler figures, it's kind of the opposite. And I don't know why.
So which is which that we're looking at?
On the left are the Doppler figures. These are the ones that were collected by the volunteers. On the right is FOF2 for all the Ionosondes in CONUS for
Right.
that day.
I would propose that the 0 to 12 on the Doppler is a lot more active because the signal level is lower. You're not really getting enough signal to get an accurate thing, and it's just jumping around.
Oh, that's an interesting notion.
Minus,
I don't like it,
signal
but
there to
it's an
measure it.
interesting notion.
On the Doppler?
On the Doppler, yeah.
That could certainly be true, probably like during the day, right?
well,
Actually,
first
that'd
we
be
need to
better.
translate to local time.
Yeah.
Well, okay, so the best way to look at translating to local time, basically, this is all in UT. So the first half of your plot is pretty much nighttime, and the right half of your plot is pretty much daytime.
Right.
So your dawn transition's happening right in the
Yeah.
middle. That's
Is
true
that
of
what
these
your
plots as well.
red line is?
Mm-hmm.
Yeah, and the ones on the left are what I'm referring to, that there's not enough signal there really to grab.
So
the
you're
station.
showing.
During
So
the
what's
day.
the question? Is there more Doppler at night or during the day that you're seeing?
Well, I think the Doppler at night is probably true because, especially if you look at a number of those plots, especially in the top part of the figure, you see coherent wave structures. Like I can find peaks and valleys that happen in one station and then match this station below it.
Yeah,
Right.
like for instance, take a look at these three together.
Right.
See
They're
how you've
three
got like
independent
peak, peak,
stations.
peak.
Right. That's like what we're seeing in the AM Doppler measurements.
Yeah.
And that happens of course, we have kind of a disadvantage. We're not recording during the day. And I think we should be. So we can't really compare daytime. But you would think that daytime would be more stable.
The lower frequencies, David. I made some simultaneous recordings at 2.5, 5, and 10. And at 2.5 and 5 were very turbulent at night, just like she's showing here. But at 10, it was turbulent day and night.
And I want to highlight that that's Steve making those from Texas, where he's got very different propagation paths. So his daytime WWB is a heck of a lot more audible than ours is in Cleveland on pretty much, all the frequencies. And also his midpoint is going to fluctuate less.
Right.
So that's a big part of, that's why when you look at this, right, if you look at the little tiny, and again, I apologize for the eye chart, this column of maps, right, you can see that they're all arranged by longitude, going from, following the terminator. And so if you look at two lines that are next to each other, they look quite similar. But if you look at, two lines on the opposite side of the country, they really won't.
David
in terms of those
McGaw.
day-night trends.
David McGaw, do you have AM Doppler measurements for that day?
Which day is this?
October 1st, 2019, full UTC day.
Let me take a look. I presume we do. And just a minute while I get this up. And the date is what again?
October
10/19?
1st, 2019.
Oh. And is that UT you're talking? We kind of span the night.
Yeah. So it's going to be, yeah, UT midnight to UT midnight on the 1st is what I have here.
Yeah, the data that our database starts in July of 2019. So
Okay, so you should have something for October.
Let me see. Let me bring. So what we call, ooh, shoot. No, we were down during that period. Ouch.
Oh, well.
Oh no.
We have a break between September 29th and October 5th.
Well, so for other
no, that's
purposes, though, while you
2020.
happen
Wait
to
a-
have it up.
That's 2020.
Oh,
Let me
Actually-
take a look at
oh.
19.
And let me, while he's doing that, I'll see what I can bring up on the super.
Oh yeah, got it. Let me
Hey.
see.
yeah.
Yeah, we got, looks like we have good data for, so is this the starting at 0 UT, the first or the second?
The 1st.
0 UT the first would be actually our 9:30 data.
And actually, Kristina, I actually have, there's a tool that I actually wrote on the Virginia Tech SuperDarn website that might actually give you the figures you need if the data is there.
That would be darn convenient. You want to share your screen and show us?
Well, why don't, sure. So the question first is the data there? So for all of the people who don't know too much about SuperDarn, this is the SuperDarn, Virginia Tech SuperDarn website. And what I'm going to do is I'm going to look for range time intensity RTI plots. So I can go down to SD data plot tools, and I'm going to hit range time plot here. And this little window here shows you what look direction you're going in. So I want to say, where do you want me to look? We probably up and down the East Coast, right? Because you have stations both on the East Coast and on the West Coast.
Yeah, I have a good spray along both, really.
Actually, if we cut this way, you're going to get like you'll be getting the midpoints in between WWV and here, which is exactly what you want. You want those midpoints.
Sure.
All right. So let's see. So this is 2019, October 1, start 0 UT, end 24. And just so you know, if you click this beam, it changes what direction this thing's looking in. So you can actually see where you're looking.
Oh, that's fun.
Yeah, so it's kind of nice. This Sebastian, I think it was Sebastian did that. He did a nice job. Okay, so fit ACF, north beam 7, channel mono. Let's see, that's all okay. And type, we can actually do, let's do ground scatter geographic. And we want to, let's plot ground scatter only. No data found. Well, that's unfortunate. All right, Blackstone. So there's nothing for, if there's nothing on beam 7, there's probably nothing on any of the other beams. Okay, let's try Wallops Island. Let's see if there's no data found. Okay, let's try Kansas. So that will be Fort Hays East. It's thinking. That's better.
That is good. Yeah. Is there an API for scraping this to just see like what data is available for a given day? Hey, there we go.
Yeah. Okay. Great. So, all right. So we're looking at ground scatter mapped coordinates. So we really care about is the power parameter. We don't care about the velocity. So power is actually like signal to noise ratio, and we want to look. Let's start by looking between 40 and 50 degrees latitude. So I'm going to change, let's turn off velocity, and I'm going to, okay, coordinates. So we're going to go between 40 and 50 degrees latitude, and then plot. And okay, good. So yeah, see all this wavy stuff here?
I do, yes.
Those would be the same. The mechanism that the radar is sensing this is the same mechanism that essentially that you're seeing Doppler shifts. So it's seeing that refraction go up and down or that path length change. But it's seeing it in the power instead of, it's seeing range focusing. So this there's a good chance this will match up with. But here's the problem again. This is only during the day, and you see stuff at night.
Well, I'm looking at, you said this is just after noon at the beginning. I don't know. It looks a little like some of the squiggly things that I have. I'd have to like.
In the afternoon.
Yeah.
Yeah. So the
I'd have
thing
to get
is,
it into closer to tell.
yeah, the way they run these, the frequencies they choose for the super darn radars usually means that you only see the ground scatter during the day.
Mm-hmm.
So, but now, yeah, so now your question is, does the frequency of this up and down, say, match roughly the frequency of your up and down?
Why are you looking at ground scatter and not ionospheric scatter?
Let's see. So ionospheric scatter means that ionospheric scatter means that you would actually be hitting some irregularity up here, and you'd be sensing the velocity of that irregularity moving.
Okay.
Okay. Ground scatter, you're going up, coming back to the ground. And as the traveling ionospheric disturbance moves through, it focuses and defocuses the rays. And then as this moves across the radar field of view, you see this focusing and defocusing move as well. And so that's the pattern you're seeing. This is a simulation of actually the radar we're looking at. So here what you're seeing. Codec unavailable. Well, that's unfortunate.
Aw.
I know I have. Let's try this version of it. I know I've redone this. Yeah. Hey, look at that.
Cool.
We can display swap. So now up here, this is actually a perturbed IRI. So I took the IRI and I put a fake traveling ionospheric disturbance through here. And so this is a horizontal cut. This is the vertical cut. And you're seeing that, and then you're looking along this beam. And down here, this is a simulation of the data display we were looking at on the actual website. So as the TID comes through, you see these swooping figures where you get the bright spots are where it's focused, and where you have white or no reception, that's where it's defocused.
Gotcha.
So what I think I'm figuring out is as a ham observer here is that you're trying to extract what's causing these TIDs from, say, the normal diurnal variation, pull it out of the noise, so to speak. Is that correct?
Yeah, well, what we're trying to do right now is we believe we see TIDs in Kristina's Grape data. And she wrote a paper and submitted it to an IEEE journal saying, we have this data network that's able to collect these things. And they're saying, okay, great, but how have you actually compared what you're seeing with another instrument or another, model to
And I said, I'm out of paragraphs. That's in future work. And they didn't like that. So they want at least a taste before we continue on.
So they're trying to, so we have to convince them that we're not just making these numbers up. So we're looking at different ways of doing that. So one approach of doing it is by looking at these things called ionosondes. If you write about an ionosonde in the IEEE journal, the IEEE people will be like, oh yeah, we understand what ionosondes are. We know how they work. That's if your data matches that, great. So that's one place we looked. Then there's another place where we're looking right now is something called SuperDarn, the Super Dual Auroral Radar Networks. Similar thing. SuperDarn radars have been around for 30 years. There's a whole body of peer-reviewed publication literature about them. If you go compare your data to the SuperDarn data and it matches up and you can explain things in terms of that, they'll be like, great, it matches something we understand. And similarly, there's this model called the International Reference Ionosphere model. It's an empirical model. But if you can show that your measurements are consistent reasonably with the IRI or some appropriately scaled version of it, they'll say, great, it passes the sanity check. So we're looking for at least one of those three options, or there are options 4, 5, and 6 as well. But these are kind of the ones that we think we have a shot at doing. The other thing, back to the references I was telling you about, Kristina, some of those, like they specifically say that I think that one I sent you specifically says, TIDs are expected to cause Doppler shifts of up to 0.5 hertz. And that's roughly what we see. So in your discussion section, you can say this signature is consistent with the description in this paper and provide a peer-reviewed citation. And again, that's more ammunition that says, okay, even though it's not exactly a 1-for-1 what they asked for, you're not doing something that's completely off the wall. What I was wondering, when you had this figure up, and we saw the more TIDs in the night, and it's quieter over here, and it was the opposite for what do you call it? It was the opposite for the ionosondes. I was wondering, Steve was saying that, well, your instrument's oblique, right? So you might be more sensitive to a different part of the ionosphere here than the ionosonde is, just picking off FOF2. So your obliqueness may mean that you're actually sensing something different than the vertical ionosonde.
Yeah, it certainly would. I've got data from that night, but we're not seeing very much. But of course, we're over on the East Coast.
Well, this over here, so this is the East Coast, David. So this is what the East Coast is seeing.
Yeah, though what you're picking up is the Midwest ionosphere.
Yeah, it's the Midwest. That's right. So actually, Kristina, I mean, they didn't ask for it, so you're not going to put it in on this. You're not going to revise it, but like putting the midpoint in, like the actual sensing point, and making that.
Oh, that's a swell idea. Well, there is a problem with that, and that's that it moves. So if I were to do that in a way that would
you pick the average for the entire day?
I could pick the average, or I could take the set of points and I could plot it across it.
Yeah.
And that might be something as you say, that's definitely outside of scope, but it's a really good idea for the next time I make these plots. I'm going to make a note of that. But if I wanted to do it in a really sophisticated way, I would animate the whole thing and have that move. But yeah, that's a good idea.
Which animations are great, but they don't get actually put in the paper.
Yes. No matter how much GRSL wants to be able to do integrated visualization things, and it's part of their charter and everything, you can't print them. So
That's right.
You could. You just take a bunch of them and you do the fanfold.
That's right. Go print out your flip book.
That might actually justify how much these journal subscriptions cost.
Oh
Yeah.
my gosh.
All right,
Nathaniel, could I share screen for a
Yeah,
moment?
go ahead, David.
I'd like to see these.
Let me see what I can bring up. Now, where'd it go? I have too many things open. Just a minute. Oh, I see it. I just saw it. Da-da-da. Oh, there it is. MD4. Let's try that one. This is the raw data that we get, which is a plot. This is the vertical is just actual AM radio channels. So between 2 and 3, that's WGY coming from Schenectady. This happens to be Jenny Jump data, but we have receivers scattered around the Northeast. And so we're primarily looking at this lower one at 3, but they're roughly ordered in frequency. So this is page 1. If I can get it to switch pages. So, 0 UT is down at the far side. Is it gonna switch for me?
Yeah, I think I'm trying to figure out how we would relate this to what Kristina is seeing.
Right. This is interesting. I should be able to, oh, wait a minute. I can't, yeah, there it goes. There's page 2. So this is getting into the nighttime. And we do have to get some of the transmitter oscillator variations out. So some of this might be that, but we're not really seeing a lot of activity that night. Let me try one more page. There.
But aren't we at least a couple orders of magnitude different in frequency compared to what Kristina was looking at?
Well, this is from like channel 3, between 2 and 3 on this is 810. And the highest frequency is 1560. Of course, I think we've re-centered some of these frequencies because the one, the very top is off on the edge of this plot, but the data is there. But we had talked about having our student, Claire Trope, talk to, compare this to the 5 megahertz Doppler data. So we should probably get you guys talking.
Yeah, for sure.
Yeah. I mean, presumably.
And she has much better plotting routines than this. This is just the raw grayscale that we send back each night.
Because like I see it between 8 and 9, there's a lot of detail in there. It's just hard to see here.
Yep. So she does much better enhanced plots, and actually has a frequency tracker that she runs through here. So if there are nights that you want to compare the data, that would be the thing to do.
Yeah, I can definitely shoot her a link to mine. Bye, Bob. With the data set and so forth. I do see some, if you go back to the October 1st data set, I think it was on 3.
Well, this is all October 1st.
Oh, okay, maybe it was earlier then. Sorry, the September.
Let me see if I can.
thing can
Well,
do?
it's showing September 30th, but that's when we triggered it.
Okay.
And then it
so
turns, the clock turns over that night.
Gotcha. Okay.
So this is, we trigger it like at 2100 hours the night before.
It looks like you do have some quite periodic variations on some of these.
Yeah. Well, some of that you have to realize that the carrier frequencies are not exactly stable. So that's one of the reasons we have receivers at different places, including one sitting at Schenectady right next to the transmitter. And that's the one, this channel 3. We do know that that has some ripples.
Gotcha. So then the one that's sitting next to it, you can use that to
We
isolate.
use that, yeah, we use that as the carrier reference.
Got it. Okay.
And can back out the variations.
Well,
Hey,
yeah.
what do you think you're seeing? What do you think you're seeing in 5?
Actually, one of these has no set signal in it. It's a, not really sure if that one.
5 does seem to have a bunch of.
Well, between 5 and 6, you mean?
Yes.
That one. Something's periodic.
If it's almost so periodic, it's almost suspicious.
Yeah.
Well, I've seen this and trying to figure out what receivers I can and can't use for this kind of work. And I've seen that kind of ripple correlate with the cycling of the cooling fan.
Yeah, well, it's not in our receiver. We're GPS locked.
But it might be in the transmitter.
But the transmitters do have oscillations. But if you see oscillations up and down, it's going to be the ionosphere, not the oscillator variations.
Okay.
Yeah. So,
well, like I said, I definitely love to compare these data sets with Claire at some point, and if we manage to pull this off, then she'll have a peer-reviewed reference to go by.
Right.
But for now, I'm looking for something that I can make a direct comparison to that will appease reviewer too. So I'm kind of back to that problem.
Yeah.
And the super darn data looks faintly promising to me. How do I yoink that I need
I just looked at it more. The problem with the super darn data is you only have it during the daytime. So super darn sees all these nice oscillations during the daytime, and when we don't. So
does it see, what does it see right after the sunrise? Does it have a nice oscillations then?
Here, I'll show you
like
again.
I'm thinking kind of, 12 to 1600 UT.
Okay. I'm actually showing all of the scatter now, not just the ground scatter.
Yeah,
Sure.
actually, as you're asking that, we're having Claire take a look at terminator effects right now.
So where
in our data?
Where were you interested, Kristina?
Kind of at 12 to 1600 UT.
You do have data there, so you can see a swoop. And where's your? I have your
figure.
There
you go. Yeah, it's actually a cleaner
figures.
version for this.
Yeah, I actually took your version and I just did some PowerPoint slice and dice magic on it.
Yup.
So
I need to go. I have another telco starting up in a few minutes.
Thanks, Bill. Bye-bye.
Thank you, Bill.
7-3. We'll catch you in the
7-3.
Yeah, so okay, so 12 to 16 UT. I mean, okay, so you get this uplift here, and you get the same uplift there.
Yeah.
And then they start seeing the TIDs in the afternoon, which
might be in our data, but are like suppressed because
it's very. So, I mean, it would be these oscillations would probably be being measured like kind of right over the Great Lakes here, roughly around that area. So, I mean,
7.3, guys.
7.3, John.
7.3.
So, like any of these should, because these are all northeast coast stations, they should all be seeing kind of the same thing here, but they're not. And this festival frequency measurement data is what frequency is it again? 5 megahertz.
5 megahertz.
Okay, and so here, you know what? This probably is not the problem. Here is if you were running 10 megahertz here, you'd probably be fine. You'd probably match this. Just like over here, they don't see anything because they're running too high in frequency. See, here's their frequency. So at night they were running like 10 megahertz, and then during the day they were running, I think, like 14, so 8, 10, 12, 14, 16, 18. Yeah, so it's 2 megahertz per tick here. So it looks like they ran 10 megahertz at night, so they were above the critical frequency or above the maximum usable frequency at night, so no data. And then during the day, they were below the muff, so you get the ground scatter. Here, we were below the muff at night, so we get beautiful TIDs. And then during the day, you're getting D region absorption, so you're not getting into.
Because you're like too far below.
You're too far below. You're not getting up to the F region here, I think, and that's why. And we think these TIDs are in the F region.
Yeah.
So, but you do see this transition here. So you do see the same little swoopy thing.
Right.
That fits with some of the other things we've seen already, Nathaniel, that the reason this 5 megahertz is quiet during the day is it can't get past the D region. And I think all that variability happens up in the F region.
You don't have any 10 megahertz data from that day, do you, Kristina?
You know, I actually do, but I don't know that I want to widen to that because I'm kind of reporting on the 5. That's what I've got in all of the data sets. 10 would take me a while to dig up.
Is it hard to get plots that look like this of the 10 megahertz data?
I don't know.
Can you get plotted enough to see if it looks like it matches this?
Yeah, I can probably do that, but I don't know if it'll solve my present problem.
Yeah, I'm not sure, but if you can do that, well then you have at least one case where it matches an existing instrument with a body of peer-reviewed literature.
Yeah.
Can I show you what I got here so I can scoot?
Yes,
Sure.
please.
Yeah, and then we should probably wrap this up. So
Yeah.
Okay, so I got everything. Let's see, what can you see? You see that graph, I guess. So there it is, transcribed into Excel. Here's
what are we looking at here?
This is the festival of frequency measurements of my data between 10 and 15 Zulu on 1 October.
Okay.
So this is the dawn transition.
Okay.
Let me go to this picture. How do I change from one picture to another?
That's why I usually just share the entire desktop and not a single window.
Well, how do you do that?
I see that you're on a Mac, so I cannot help.
It's the same way on the Mac. You just you pick the thing that says screen 1, I think. It either says screen 1 or desktop 1. So stop sharing, Steve, stop sharing.
Well, you know, every time you change something up here, that main screen goes away. Oh, here it is right there. Stop share. Okay, cool.
Okay. So now hit share.
Okay.
And then choose one that says desktop 1 or screen 1. It should be the upper left choice.
Oh.
Yeah, now we can see your entire desktop.
Oh, well, that's pretty cool.
You just have to make sure you don't have any sensitive information on your screen when you're showing this.
Okay, so here, this is the transcribed data from this.
Yeah,
Right? This is the data from,
this is yours.
what's that program called? Spectrum Lab.
Yeah.
Yep.
And so I went through and read all these numbers and fed them into the spreadsheet. Now, this thing, if I could bring up the edit picture, if I mess with the contrast,
Mhm.
I'm only going to work with this plot right here, which I think is the F layer. I think this is from the E. I think this is one hop F layer, and it kind of disappears right here. But if you change the contrast, it real dimly continues on down here. And then there's these, not one really, but two things up here. Can you barely see this dim blue line right here?
Yeah.
If I change the contrast, it shows up quite a bit stronger. I think that's two hops,
Hmm.
that one. But if you look real closely, there's yet a third curve here, and this actually pulls down inside it. So this is a real complicated morning. And I don't know why these two are close together. Is it possible that that the F layer is split and one's from one and one's from the other?
I suppose it's possible. Could be like F1, F2.
Yeah, well, I mean, why would there
or
be-
ordinary or an extraordinary?
Yes.
Yeah, that's true too.
Are they that close?
They would be very close.
Okay, that may be it. That may be it. Thank you. So anyway, because there's some things I don't understand going up. Well, I don't understand a lot about any of it, but because there's so much complexity with this stuff here, I'm just going to do the height calculation from the main one.
Yeah, that makes sense. Yes.
And I've just about got it all ready to go.
And
Now
that's
that
the
I've got
thing
it in spreadsheet form, I can do the math on it.
Yeah, that's the thing. You'd probably seen Kristina's far lap simulation too.
Yeah, so to clarify, I think if I've got it right, Steve, what you're doing is let's see, you're integrating your data because the Doppler shift should give you the derivative of the ionospheric height. Do I have that right? Yeah.
Yeah. As the ionosphere changes, Doppler happens as a function of the rate of change of height, and you have to correct it. You have to convert path or height into path. And I'm using just a flat Earth model, similar triangles, because I don't have any other way to calculate the more complicated curvature of the Earth, which isn't much. I mean, we're talking about 250 kilometers height and 1,400 kilometers path length. It's really a squash triangle. So the error from going between flat and a little bit of a curve really isn't very much. So what you actually deduce from the Doppler, you convert Doppler into path velocity, and that's the whole path. And then you have to convert path into height with geometry.
Okay.
So our hope here.
This was the whole process.
Yeah.
The equivalent path velocity from Doppler data, and if you know the frequency, speed of light, you got that.
So can you go back to your plot that you showed at the beginning?
This one?
Yeah.
Or this one?
Well, I may as well have them all up, honestly. The transcribed FFM. So what you've got there is you've broken it out into your different layers. Do you have an integration?
Show up. You notice down here, this one quit right here, but it continued very dimly, and
yes.
So I continued it because it just got very weak. The amplitude got small, but the frequency kept on the same track.
Right. David says he has the 10 megahertz data for that day up. Do we want to take a quick look at that?
Sure. This is 5.
All right.
Yeah, if you have 10 megahertz data for that day, that would be great.
Yeah, it's in the form that I've been collecting it. So
Should be
Steve
pretty
Taylor's down, and
visible. Yeah.
I'll
We wanna
switch here as soon as I
yeah.
can.
Just see if there's TIDs going through the day. We can
Yeah,
get
Steve.
anything that matches.
Although, like I said, I'm a little concerned about, showing off the 5 megahertz and then showing the 10 megahertz as an example, but
So here the
Okay.
black is Doppler, the red is relative signal strength.
That might be. You could actually probably low pass filter that a little bit. Get out.
It has been, and all of my graphs are filtered the same way. I have the second by second data.
Right, but you can probably low pass filter to remove things with periods shorter than 15 minutes.
Right. This is, my memory is that this is about 10-minute filtered.
Yeah.
I can't tell you offhand, but I think that's correct.
Okay, hold that plot. I'm going to share my screen, but don't keep your plot available.
Okay.
All right. So back to this. So this is the interactive range time plotting tool. There's also another tool here called dynamic FFT tool.
Mhm.
So we can put in a lot of the same information. We're going to choose, let me see if I can put these up side by side so we can get the same information on. Okay. So I'm going to choose Fort Hays East Radar. And then I'm going to choose, let's see, it looks like we looked at beam 11, so I guess we'll do the same thing. We will have to pick a range gate, but we'll do that in a minute. And so we're going to pick a date. So we're going to do 2019. We're going to do October 1. We'll keep the same start and end time. We'll do the same plot all scatter. We can do a linear, let's see, I don't know, subtract average. We're gonna do the power parameter. Time series. Let's just leave it at that for now. You have to iterate on this a little bit. So let me hit plot. But I think this one will actually give you a line plot. The backend code for all of this is all IDL, by the way. All right, so here's what you get with this tool. So here you get the same RTI plot you got over here. And then you see this little dashed line right here? That is the line cut of what you see down here. So it pulls off those colors and then it plots it as a 1D line. And then, so we really want something that goes right through the center of here. So this is like range gate 40. So I'm going to change this to gate 40.
Okay.
I'm going to hit plot again. Okay, so average subtracted. Okay, I guess this line doesn't show you that, but now you know you're going through range gate 40, so you know that it is going through here. There's no visual indication of it, but that's where this data is coming from. It's coming from straight down there. Why don't we adjust this to go between like 20 and 45.
Okay.
So you see it's a little bit of an iterative process.
Yeah.
RTI plot.
So what's our end goal once, well, I'll let you get these in and then I'll ask you while we're watching the spinny thing.
Okay. 22.
You know, Nathaniel, while you're doing that, your ice pick there is rough. Well, it's not too far from our path to CHU. And I have an interesting data set from 7.85 megahertz CHU now. It's distinctly different from the Fort Collins beacons.
Mm-hmm. So what I'm trying to do is my goal is to get this thing visualized in such a way that I can comfortably see the wave here and here, and then actually be able to be convinced that we're actually seeing the periods that we're looking at. So I think I clipped off too much of the top here. So I'm going to add like 40.
Okay.
So I just keep going through this. And then my goal would be to have the line plot there look as close to David's line plot as possible.
Right. Can you change the time parameters of this?
Yep.
Yeah, like start maybe at noon and then.
Yeah, that would help a lot. I might go up to 45 here. This is starting to look a lot better. Right, so now you can see this go through. This looks like almost, what do you say? This was like maybe the dawn transition. Here's your TIDs going through here. We're actually still probably a little high. We probably really want to be going right through this range gate here. So this is range gate, say 33, but straight through here. So I'm going to change this range gate over here to 33.
Okay.
Hey, Nathaniel.
Yeah.
You know those two little pre-dawn oscillations that showed up in my FFM data?
Yeah.
When Kristina had the plot up that showed a whole bunch of them, I was looking at those and they showed up in several others.
They do, yes. I'm looking at them now.
So if that's a TID, by looking at where those stations are, can't you kind of localize where it was? Because it's got to be
where the wavefront is. Yeah.
What'd you say, Nathaniel?
Like where the wavefront is?
No, by looking at which data plots it shows up in and knowing what those paths are, couldn't you kind of localize where the TID was? It would only be over the paths that had that feature.
Yeah. Well, the TIDs, they generally, like the wave field often covers the entire like US.
But what in all of them?
Not at the same time. So yeah, maybe.
Well, my imagination of that is that you kind of have like those midpoints would have basically that you're like trying to fill in pixels that would be shifting, right? Because the midpoint is shifting, that's relevant. And that it would show up in some of those. But that's why I want to do the bare minimum at this stage, because I feel like I'm just kind of introducing the experiment in the letters paper, and then there's more to dive into with validating according to other stuff.
Yeah, you just
because it'd be interesting, you know, this is like
reviewer.
Yeah. I want to give them, you know, enough to justify it as a technique, but
I think I'm gonna sign off here in a minute. I promised Dev I would talk with him for a couple minutes.
Yeah.
But I think you can see where this is going now. And now we're able to start creating this trace, which goes right through range gate 33. And so now you're actually able to see the TID this way in SuperDarn as well.
Can you send me this, and is there a way for me to download the
yes, what I'll do, you can't get in order to get the raw data, you have to email them.
Well, that's not going to work on the time constant in question if that's manual.
No, and trust me, the raw data is in a format that it's not a simple format.
Roger.
But this particular web tool is very useful. Copy image, and so what I'll do is I'm actually started sending you an email already that has some of this in here, and I will also go and I will do a screenshot of
the settings you used.
the settings. Yes. Yeah, down here.
All right.
This was all written in IDL. You would be amazed at the back end that makes this thing work.
I bet I would. I also bet the little spinny thing is an old friend to you.
Yeah, I think Lassie Clausen put the spinny things in. He's the one that came. Lassie Clausen came up with the framework for super darn data. Lassie Clausen, who was a postdoc when I was there, he came up with this spinny thing and how you actually set up these interfaces to the code. And so he wrote a lot of the first code for this. I then took that and I wrote this particular module for the FFT analysis. And this is all under the hood. It's all IDL.
Okay, well, I'm going to dig into this, but I am definitely going to have more questions. So expect some emails from me.
Sounds good.
And then let's see. Steve, do you mind if we hop into a breakout room and I can talk to you about what you've been doing with IRI? Because I still got some questions on that one too.
Sure.
And I'll
right.
hop into a breakout room with Dev. I'm going to stop the recording now. I'll hop into a breakout room with Dev, and then everyone can just go when they're all done. Okay?
Sounds good.
Nathaniel, maybe we sign in our regular meeting ID.
Yeah, that sounds good. So I'll just meet you in your regular ID.
Yeah.
I'm going to make someone else the host of this. So let me stop the recording, and then Kristina, I'll make you the host of this meeting so that
Sounds
you
good.
can
And then
do
I'm leaving.
whatever you need to do.
Hey, Dev, thank you very much for the presentation, and it kicked off a lot of good discussion, so it worked out pretty well.
Yeah.
Yeah, thanks, Dev.
Thanks, Dev.
Thank you so much, Dev.
He's not here.